Hello, my people. I hope we're doing well. As promised to those who were, those few who were in class today, I'm going to go ahead and finish out the problems that I had designated for the class time today, for lecture, whatever you want to call it, on this video. So this fourth video is more like a supplement to day two or whatever, but just figured that we'd go ahead and spend a few more minutes and get the last bits of these out, and that way you'll have two full class period videos as well as four YouTube videos, complete with the scanned worksheets from all of that. That with the four old worksheets that have answer keys worked, you have gobs and gobs and gobs of material to work with in order to become familiar with these identities and be able to do these verification problems. So we went ahead and did this one in class, and this is where we stopped. And the next problem was this one. Tangent squared alpha times sine squared alpha is equal to tangent squared alpha plus cosine squared alpha minus 1. Now, the right-hand side is a little bit more complicated because it's second degree, while the left-hand side is fourth degree, but it's also three terms. What I'm going to do is, I see the fact that my left-hand side is all in terms of tangent and sine. I have a cosine squared here, but it's minus 1 instead of 1 minus. And it doesn't really matter. If I wanted to, basically if 1 minus cosine squared alpha, right, if sine squared alpha is equal to 1 minus cosine squared alpha, then cosine squared alpha minus 1 is simply negative sine alpha, right? Because when you flip a difference, you just turn it negative, okay? Well, if that's the case, then what I have here is tangent squared alpha minus sine squared alpha. Okay, well, I have a difference here. That's not a difference that I recognize as any sort of identity, but I do know that tangent is potentially, or can be thought of in terms of its ratio. And if that's the case, and this can be thought of as sine squared alpha over cosine squared alpha, then maybe I need to think about this in terms of getting a common denominator. And I'm kind of running into my work over here. I should have popped down just a little bit. But basically, if I multiply that by cosine squared over cosine squared, then what I'm going to get here in the numerator, once I combine them and factor out a sine squared, is that, okay? You got a common denominator, you push them together, and you get sine squared minus sine squared times cosine squared. Those two terms have a common factor of sine squared, so you factor it out. And then, of course, basically, you're going to reuse this right here as sine squared alpha times sine squared alpha over cosine squared alpha. And this right here is your tangent, okay? And so if that's your tangent, then you get tangent squared alpha times sine squared alpha. And there might be an easier way to do this, but the way that I saw it doesn't actually take all that much time. So cha-ching, okay? The hope is that once I get them in tandem with each other, simple as I can right here, the hope was in transforming it into a rational expression that it would reveal something new, and that would allow us to sort of recombine and use those Pythagoreans again to basically come from, because we use Pythagorean to go from 3 terms to 2 terms, and then again we used it to go from 2 terms to 1 term, right? And so it was basically 2 rounds of using those Pythagoreans to sort of get something of 3 terms all the way down to a 1-term expression. Now, that was fun. That is even more fun. So what I have here is I have tangent squared plus 1 plus tangent secant. And that's equal to this ratio over here. Okay. Well, okay. Well, that might actually be kind of helpful. And the thing is that this is one of those ones where I could work on both sides, okay? Because I automatically see the fact that that right there is going to be secant squared. And I automatically recognize the fact that this right here can be transformed into sine x times secant squared, right? So we're going to use the Pythagorean, and this is secant squared x. And this right here, since tangent is sine over cosine, tangent is also sine times secant. So we can basically put sine x times secant squared. And if we factor out that GCF, we can actually turn it into that right-hand side. Now, let's say that you wanted to start with the right-hand side. Okay, it would be a little bit more difficult, but not terribly so. You would basically just separate the fraction, right? And if you separated that fraction, I'll give you the first step. I won't actually work it all the way. If you separate it into 1 over cosine squared x and sine x over cosine squared x, sine over cosine squared is this term right here. This 1 over cosine squared is secant squared, which can then be transformed into these first two terms. And so basically that's just the same logic that I used. It's just running that logic backwards, right? Well, not really backwards, the other way, okay? Now, that one looked a little bit gross, but it wound up being okay. This one looks terrible, okay? But you have to, like I've said before, stop and think before you do, okay? And what we recognize here is that when we FOIL this out, if we were to FOIL this out, and by the way, we're going to, if we were to FOIL this out, the last term would be tangent squared. Because, I mean, basically, the whole thing about this numerator is you're looking at that plus 1 going, what the heck do I do with that? Okay? And when you FOIL out this, this numerator, all of a sudden that tangent squared winds up right next to that 1, and that whole what the heck do I do with this gets answered really quickly. Okay. Now remember, just like in the last one where I said tangent is also the same thing as sine over cosine, which means it's also the same thing as sine times secant, right? So when I look at the denominator, there's a secant sort of embedded within that tangent. So if I wanted to, I could actually factor out both a secant and a cosecant. And if I do that, what's left in the first term is 1, and what's left in the second term is sine x. Now, this right here is secant squared. And so when I transform it, it can be combined with this secant squared, which is the first term of the numerator. Okay. And again, we can see the fact that we have a tangent. So there's a secant squared that's common to both of these if I remember that tangent is the same thing as sine times secant. Okay? And if that's the case, then I can factor out 2 secant squared theta 1 minus sine theta over secant theta cosecant theta times 1 minus sine theta. And what looked like a hot mess at the beginning is all of a sudden looking very, very nice for a bit of cancellation. So this secant cancels with one of those. This 1 minus sine cancels with this 1 minus sine. And secant is 1 over cosine, Cosecant is 1 over sine, and in the same way that tangent is sine over cosine, it's secant over cosecant as well. So that is 2 tangent theta, and that simplifies nicely and simplifies to exactly what I have on the right-hand side. Okay? And so, cha-ching. Alrighty. Well, this next one isn't really all that difficult, largely because we've seen that form before. But we've seen it in terms of sine and cosine. We've seen it in terms of secant and tangent. We have yet to actually work one out of the same form that dealt with the cosecant cotangent Pythagorean and multiplying by the conjugate, which is, predictably what I'm going to do right here. I'm going to go ahead and multiply this one by the conjugate. Okay. Now when I do that, remember, just like the sine and cosine ones, and just like the secant and tangent ones, I'm going to leave this numerator in factored form. Now the whole reason I'm going to do that is because I want to eventually cancel, and factored form, like I said, is canceling form. If you actually distribute it, you're kind of messing up that whole system, right? Now, for those of you who have worked with the sine and cosine Pythagorean and the tangent and secant Pythagorean, but have yet to do much work in the cotangent and cosecant Pythagorean, remember, it's this middle column right here, okay? And we recognize the fact that cosecant squared minus 1 is cotangent squared. So that denominator becomes cotangent squared. That cancels out with one of those that's in the denominator, and as a result, I'm going to get cosecant theta minus 1 over cotangent theta. Okay? And that, of course, is exactly what I have over here on the left-hand side. So I have successfully verified. I box it, put a check mark next to it to say, yay, me. Now, let's go ahead and look at this next one. Now, anytime you have one rational expression plus or minus another rational expression, you have to be worried about this negative. Because that numerator right there is functionally the same thing as parentheses. Now, there's an easy way to deal with that right off the bat. If that numerator is also a difference, I can go ahead, what I'm going to do is I'm going to go ahead and do the distribution. I'm going to change that right there, and if I change that negative to a positive, all I have to do is flip the difference in that numerator, and I have changed the sign of that rational expression, right? Or think about it this way. If I were to factor a negative 1 out of that difference, it would flip, and that negative 1 would combine with this minus sign to become plus. Okay? And if you go ahead and do that right off the bat, then you don't run the risk of forgetting to distribute that negative if indeed it becomes necessary later. I was always the student when I was sitting where y'all are that forgot, like I lost negatives. I forgot to distribute, negatives over, over polynomials and stuff like that. So over the years, as a student, I learned little tricks that basically prevented me from making those common mistakes that I was so prone to make. Now I have two rational expressions, and I need to go ahead and get a common denominator. And so since those denominators are relatively prime, and for those of you who don't remember what relatively prime means, it means that they don't share a factor. When you're trying to get a common denominator, and the two fractions have denominators that are relatively prime, then you simply have to multiply each of them by the other denominator over itself. And then, of course, we're just going to distribute here in the numerator. And And that is all going to be over sine x cosine x. Now that right there is obviously 1. This is positive, this is negative, and those cancel out because they're additive inverses. So what I really get here is I get 1 over sine x cosine x, which of course is going to be, in fact, we're just going to switch the order when we actually turn it into this, and it becomes secant x cosecant x. And that is exactly what I have on the right-hand side. I have verified. Yay me. Okay. Now, I had a request in class because of that last problem on the homework, and of course it'll be the last problem on tonight's homework as well, to do the ones at the end that didn't look like any of the others. And really this is just a hearkening back to the inverse trig from last chapter, or what we would consider to be from the first 3-week term. Now the whole purpose behind this, I think, is they're trying to drive home the fact that any time you have two different expressions which are equivalent, meaning they give you the same value for all values of the variable, they are functionally identities, you know. So if you ever saw this in a much larger question, you could just quickly plug that in instead, if indeed you remembered this identity. But I'm not sure exactly how they want us to solve this, but the way that we actually did it in the last chapter is we need to remember that the only type of values that trig functions are applied to are angle measurements. So this is an angle measurement, okay? Now, that should make sense to us because it's the inverse sign of a value that is a ratio. The only things that get inverse signed are, let me put it this way. I'm going to go ahead and just be really explicit about it. Basically, the only things that get trigged are angle measurements. Okay? The only thing that get inverse trigged are ratios. Okay? So I don't care what is like what form the expression inside the parentheses takes. If it's sine of whatever, if it's cosine of whatever, if it's tangent of whatever, if it's cosecant, secant, or cotangent of whatever, that whatever the form of that expression inside those parentheses, that is an angle measurement. Okay? If you have inverse trig, if you have inverse sine, arc sine, inverse cosine, arc cosine, inverse tangent, arc tangent, and of course the inverses of cosecant, secant, and cotangent, I don't care what form this looks like. I don't care if it looks like a puppy dog running through a field of daisies. I don't care what it looks like. It represents a ratio. Period. The end. Okay? So while this may not look like an angle measurement, it stands in for an angle measurement. And if that angle measurement is right here, then of course x represents x over 1. X over 1. Opposite over hypotenuse, right? Well, if I do a little bit of Pythagorean theorem, I get the square root of 1 minus x squared for that other side. And if I'm looking for the cosine of that angle measurement, I'm looking for the adjacent over the hypotenuse over 1, which of course is 1 minus x squared underneath the radical, just like it is on the right-hand side. This is a skill that actually will come up in calc, so it is good to remember this, and it is good to revisit it every once in a while. This one is at one time a little more difficult, but also a little easier, because sometimes when something doesn't look like a ratio, we don't think of it as a ratio. The part that's easier about this problem is that that actually looks like a ratio, okay? And since it's being tangented, okay, that is our theta. And since we are being given the cosine ratio in terms of representing that theta, I know that it's going to be x plus 1 over 2. Now, if I want to solve this over here, by the way, it's this right here, let's call this b, okay? And remember that it's just x plus 1 squared plus b squared is equal to 4, or b squared is equal to 4 minus x plus 1 squared, or b is equal to the square root of 4 minus x plus 1 squared. Ta-da! There we go. Okay, so that's no longer b. We're going to basically label it as 4 minus x plus 1 squared. And therefore, basically, our tangent of that theta is going to wind up being the opposite over adjacent, which is 4 minus x plus 1 squared over x plus 1, which indeed is the same as it is on this side. Like I said, I'm not exactly sure what the author of this textbook wanted, how the author of this textbook wanted us to verify it. But that's the method that we used in when we actually dealt with inverse trig in terms of coming up with those ratios, right? So if you start off with a ratio and then you inverse trig and then you trig, you should get back to a ratio. Now obviously, because these are different trig functions, this is arc cosine, which is then tangented, you do get a different ratio than the original one that you started off with. But it should make sense to us that if anything is tangented, we should get a ratio, which is exactly what we have right here. Okay, guys, that kind of brings us to an end for the videos for this section. Tomorrow we're going to start dealing with using those trig IDs to solve trigonometric equations, which if you haven't sort of boned up on your factorization skills and formulas, you may want to go ahead and look those over because that becomes part of it. But as always, if you have any questions, please do shoot me an email or shoot me a message on Teams, and I will try to get back to you quickly. Bye.